You wouldn't believe how hard I worked on that one sentence in my CV. But it's the second time somebody reads it out loud, so I must have hit a note there. Okay, I'm going to talk to you about how Earth's mass changes, how we observe it, what the challenges are, why we do it, and some messages hopefully that will help all of us making most of geophysical data, which for me is anything that is global, can be collected by global networks of seismometers or satellites such as for gravity or the magnetic field or any other field that you can think of. And I'm mixing and matching work, ultimately much of it in terms of theory going back to my late supervisor Tony Darwin, then also Marc Wieczorek in Paris, who is a planetary scientist that I have learned a whole lot from. Xinshan Han is a guy at NASA Goddard that I worked with extensively. And then some graduate students, Jessica Hawthorne, Dong Wang at Princeton, Lei Wang at Ohio State, and then some Princeton postdocs, Chris Harrod, Kevin Lewis, and Alain Plattner. And of course, as they say, all the mistakes are mine, but the credit goes to them also. I'll give you a very brief outline on the GRACE mission, which is probably familiar to most of you, but it won't hurt to repeat because it's really an amazing type of a mission. And I'm going to give you a little theory also about the general problem of analyzing noisy and incomplete data distributed on the surface of a sphere, which is basically what I think of as global geophysics, is making something out of observations through modeling, which is invariably, noisily observed, those data are, and incomplete in terms of coverage or bandwidth or limitations of the instrument. And then I'm going to apply this to an important part of the Earth's mass balance budget, which is what is happening to our ice caps. And so our case study is what's happening to Greenland. And you may have heard, probably even from the people in this department, what has been happening to GRACE in terms of constraining the meltwater budget of Greenland and Antarctica and some mountain glaciers. It's been in the news over the last 5 years or so. There were nevertheless to us some remaining problems of a statistical and a modeling nature to work out just exactly how well we knew what we thought we knew about how these things are melting. And I'll give you some ideas and some solutions to that. I cut out the earthquakes, but those of you who wanted the earthquakes from the title, they can stay later. I'll put them back in. I switched them to a few slides on the spectral properties of the Martian magnetic field, which is just another potential field that's been noisily and incompletely observed that we can use to make geological and geophysical inference. And then I'll, sum up. So this is Earth's gravity field reduced to an anomaly, which we call the free air anomaly, which essentially means it's reduced to the same level, and we have not taken into account mountains and valleys and their masses, but we've just referenced the data to the WS84 geoid. Now this is the EGM 2008 model, expanded in space and not projecting so well here, but it's literally just in meters per second squared to the 10 to the minus 7th here or so. So of course this is what we've been doing for decades, is to try and ever better map the Earth's gravity field, because we see plate tectonics right happening before our eyes. We see the Hawaiian Emperor mountain chain, we see the whole subduction zone system of the Pacific, we see the interesting ridges and trenches and mid-ocean ridges, transform faults. Of course, this is probably half the story of what we know about plate tectonics ultimately came from observations like this, and then combined with seismology. So this is a very spatially variable field, and we've spent decades of satellite mapping to trying to get it at its most precise and accurate. But of course, GRACE is about how the gravity field varies over time, and over a time scale of years to now about a decade. So the idea is simple. One satellite is in orbit, another satellite is in orbit. They both know their position using GPS. They both record their acceleration. And they both record the distance between the satellite as the whole pair moves around the Earth about 10 or 11 times a day, shooting a microwave beam at each other and measuring their evolving distance. And as the leading satellite feels a mass anomaly, this distance gets larger, and then the trailing satellite catches up with them, with it, and then the whole system repeats. And so it maps out every little bit of potential perturbations as it orbits, which we get from analyzing the time series of this evolving distance together with their positions and their acceleration in various combinations. So, GRACE, in its mission statement, says it's going to map water masses and their effect on the gravity field, and of course it was sold and primarily useful to global climate change, because what happens to the water is what happens to climate. This microwave ranging system apparently measures the distance to detects a separation change of about 10 microns. That's the number I was looking for, which is about 1/10 of a normal human hair over a distance of 220 kilometers. So this is a huge feat, which in later missions has actually already been surpassed, such as on the Grail mission on the Moon. This is now a laser that shoots from one satellite to another. So we have no trouble measuring very precise distances. The question really comes in when, what do these numbers do for us? What does that ultimately translate to in terms of spatial resolution with which we can see the changes in the mass of the Earth? The temporal resolution is this on a daily, hourly, weekly, monthly time scale. And then also this question that I'm particularly interested in is, what do we know in terms of wavelength? Can we break down this type of signal in terms of its spectral characteristics? Because very often, by looking at the distribution of energy over wavelengths, we can see right through to the geophysical processes going on, and we can model them very effectively. So hydrology is a big application of GRACE, and without belittling it, it's a big signal. So what I'm showing here is 1 month of GRACE, October 2008, and subtracted from April 2009. And I'm only showing you the large-scale structure. In terms of spherical harmonic degree, the basis functions used to map have a bandwidth of 18 degrees. So the rough spatial scale that you see, there's about 400 terms in this type of expansion. And when you just subtract, doing nothing else to the data, 1 month of the solution from another month of the solution, what's the gravity in April versus the gravity in October, you see the large-scale pattern of hydrological change, which you can then correlate to, let's say, whatever happens to the seasonal signal in the Amazon, or the Orinoco Basin, or the Congo Basin, or the various waters that drain into their various oceans. And I don't know how well you can see, but you probably also see large stripes running right through the solution, which are, of course, a problem, and it's not something that is physical. This is already a part of the noise that I'll be trying to get rid of. But nevertheless, over large areas, over months apart, and for the big signals, the hydrology is really right in there. And I'm going to stop worrying about that for the moment. Here in this next picture, I'm expanding the same field. Now, this is 1 month of GRACE, December 2000 I forget. It doesn't actually matter. Yeah, it doesn't say 1, but the mission wasn't up then, so I know it couldn't be 1. It looks like 1, doesn't it? So this is the free air anomaly. Now I've filtered this. I've put in more spherical harmonic degrees, so we see smaller scale oscillations. This is to about L equals 60. And here we are back at the signature of plate tectonics. This is just GRACE doing its job measuring the gravity field, and in this month of December 2004 is what it is. That's the 4. It's already showing again the trenches and the ridges and the various features that ultimately teach us something about Earth structure. So whatever is in there is what we're going to try and look at. Well, take a look at 1 and 2. I'm flicking back between December 2004 and January 2005, and you're not supposed to see anything, right? So a lot is going on, but at this scale, you don't see anything. So the scale here is 10 to the minus 4 of the SI unit. And I'm going to show you one earthquake. This is a huge earthquake. This is the Sumatra-Andaman earthquake, which happened in December 2004. And this is my seismological prediction of the gravitational potential perturbation due to that earthquake. A little more here, a little less there. This is once again in the same gravity units of a free air anomaly, refugeoid. And compared to this monthly signal here of January 2005, 10 to the minus 4 of units, this gigantic earthquake has a very localized perturbation to the potential, but its unit is 10 to the minus 7. So we're about 1,000 times smaller than what's visible to the naked eye. That nevertheless, now I go back to flicking between January and 2005 and December 2004. In between those pictures, the earthquake has happened. Can I find it? The answer is yes. And that's the prediction of the magnitude and the size of the signal, which is known to be about 1,000 times smaller than anything that's in this easily observable picture. So nevertheless, we're going to try and look for these, and I have some successes to report. So how can we look? Well, let's do the most basic thing we could do. Let's just subtract the January 2005 and 4. I showed you those 2 months. They look like plate tectonics. You couldn't tell the difference. Well, here's the difference, and it's full of stripes. So this is the first manifestation of the gigantic noise that Grace suffers from, which is basically a very correlated error structure as the satellites have a preferential direction in making the measurement and doing the orbits. And just subtracting the 2 best solutions of those 2 months separated by 1 month during which this tiny but large earthquake happened just gives you a bunch of noise with which we can't do anything. Now that's at the full resolution of this L equals 60. So we see about 60 of these stripes in this thing. So can we maybe do filtering? Well, let's take this down a little bit. Now I'm stepping down through the frequency range and giving you coarser and coarser, larger and larger spatial scales. This is L equals 50. Of course, you still don't see it. L equals 20, 40 that was. This is 30. This is 20. You're starting to pick up the hydrology again. And, shout if you saw the earthquake, but you can't do it by differencing and filtering. You have to do a very, very careful job. So, from this simple experiment of just looking at the data, okay, well, I'm going to forget about the hydrology because I hope to have made the point that is fairly easy to see. Large signals, low spectral degree, so broad, long wavelengths, is more or less straightforward to extract from the background. Earthquakes, I'm going to forget about this for the moment. In some of my other talks, I actually return to them, and if you want, I can show you that. They did appear hopeless. Nobody ever thought of looking at earthquakes from Grace for a long time. It wasn't in the mission plan. But nevertheless, we are able to pick them up, even at this 1,000th type of threshold. And I'll show you some examples of looking at the climate signal, which is about the longer-term, multi-annual trends where I'm going to try and answer the question, how well does Grace detect what may be going on with the world's ice caps? So this whole business of differencing and filtering and these spurious stripes that show up, this is all well known in the community, and there is a whole industry devoted to designing filters to take out these known artifacts. So you can find 5 to 10 to 15 papers on filtering techniques to enhance the signal-to-noise ratio, to de-stripe, to get rid of the correlated errors, and to come up with a clean signal. But what about Greenland? I'll show you in more detail what my worry is. I'm going to tell you in a brief moment what goes into the estimation. So there were, in the literature, vast differences in people's numbers of how much mass Greenland really was losing on a decadal time scale, factors of 2. But all of these authors, we do need to make a lot of corrections, but the problem really didn't lie in the geophysics. All of the authors agreed on, if you take out a bit of ice, instantaneously there is an elastic rebound that goes on, and so you can model that using love numbers, and some of the people in this department are very into those things. Authors also more or less agree on viscoelastic, the longer-term effects, the post-glacial rebound corrections. And even if they didn't agree, because various models disagreed, everybody can subtract the effect and can, when they pick the same model, they should get the same result. So it wasn't there that the discrepancy lied. But the authors really disagreed on something that I thought was much more interesting ultimately, which was on a statistical, mathematical side of how to really deal with this correlated noise, this filtering, this leakage of unwanted noise into the wanted signal, and how to properly incorporate the statistics of the estimation as an inverse problem into these solutions. And so, I don't know if you teach this to your students, but when you do a problem, you need to pick a basis. Is it a pixel? Is it a spherical harmonic? Is it a sine or an exponential? In gravity, is it an ideal body? Is it a mass-on? There are tons of different ways of representing and modeling the data, and all of those choices have statistical implications. And this is where people actually all did something different. Some of them modeled in mass-on, some of them as individual pixels, some of them as global basis functions. So what I wanted to study was how these mathematical choices of treating the data influenced the data statistically, and thus the results, and led to these vast disagreements. So here's the problem in words. We have some data. It's collected over some region R, or it's collected everywhere and we really only want to know something, make inference about a region R. And I know the data is consisting of signal, which I want, and noise, which I want to get rid of. And I'm going to make an assumption that the noise is a zero mean process and that the noise itself is statistically uncorrelated with the signal, which is a reasonable assumption. And I'm going to model the noise by trying to get an idea of its covariance structure. So, like hopefully all of you, you've got data and they're noisy and they're incomplete, and ours are in the sphere, and we're trying to do a proper inverse problem for finding the signal. So in symbols, our data on the sphere is a signal on the sphere plus a noise on the sphere if it's inside of the region of interest, or it's either unknown or we don't want it if it's outside. I assume that on average, with these brackets here, the noise is zero, and on average, the cross-correlation between the noise at one point and the noise at any other point vanishes. And I'm going to need and model the variance of the noise in this representation. How is the average correlation of the noise in one point with the noise at another point? So nothing fancy, but they may be new symbols to you. And we're going to, of course, work in spherical coordinates on the surface of the Earth. So we'll be working with spherical harmonic basis functions. So to those of you unfamiliar with them, they are like Fourier series wrapped around the sphere, like sines or cosines wrapped around the sphere. X, Y, Z. Omega is my sphere. Two coordinates. Theta is the colatitude. Phi is the latitude. And the spherical harmonics, of which I'm showing one of them, are a number of solutions indexed by integers L and M, degree and order, functions on the sphere, and they're an orthonormal basis on the surface. And from geodesy to global seismology to geomagnetics, they were popular bases to represent global signals. Also in chemistry, obviously, and various other fields. So what's the key property that we like about spherical harmonics, other than that they're pretty looking, is that if you take one, you take another one, a different one, and you integrate their product, that it vanishes if they're not the same, which is this orthonormality here. And that means that we can use an expansion of the unknown signal as an infinite series of spherical harmonics, and our objective will be to determine those expansion coefficients from the data as an inverse problem. So what's now the problem? This is what we want to do. We want to explain our data in some mean squared, least square sense. And it's a hard problem because we're working at an altitude above the source with a potential field. So the traditional way of formulating it is by saying we want to find a signal that agrees with the data such that the sum of the squared residuals over the region of interest is as small as possible, so we have the best possible match. But knowing how hard it is, because actually you can show how easily it quite literally blows up due to the effect of needing to go down from the satellite altitude to the source level, and to the fact that it's incomplete in its observation domain, we're going to modify the problem by saying, okay, fit the data as well as you can in the region, and outside keep whatever signal we don't want, don't need, or have no information about to a minimum. And so we have a typical least squares in the data, least squares in the model norm with some variable trade-off parameters. And essentially all of satellite inversion is to try to solve some problem like this where you determine some optimal level of data misfit and model regularization. And of course the statistics itself of what you know or don't know about the signal and the noise dictates this trade-off of data and model norm. So this eta here is some regularization parameter. But when the data are only known in a patchy region, and this in geophysics might be Africa and India, or this may be a polar cap in astronomy, or in cosmology this may be anything but the galactic plane of observation, is maybe Greenland, as in my example here, because the data is restricted, or the model region of interest is a small portion of the sphere. If we stick to this formalism of using these spherical harmonic basis functions, we immediately run into the problem that this orthogonality, take a different one and integrate over the available region, it's no longer orthogonal. And so I don't know if you're crying with me about the loss of orthogonality, but it's kind of a big deal to have lost something that was so handy to begin with. And so it actually is a big deal that this is no longer the product of Kronecker delta functions, ones or zeros. This is now actually a full matrix for every degree in order, and every other degree in order. You have a coupling between all of the harmonics together, and all the subsequent estimation suffers from this loss of orthogonality. And this so-called leakage of pieces of the signal showing up in the wrong place and the noise coupling across a wide variety of degrees is what happens when this property that used to be all of omega, and this was a delta function, is lost. So what we're going to try and do is we're going to try and turn this to our advantage by taking this loss of orthogonality operator and try to find its eigenfunctions, because that will be a proper basis to do the modeling in, as I'm going to try and show you. And so there is a long series of papers, and they're long papers, on how to do the proper diagonalization of this operator. And we gave them a name because actually it's what people did in the 50s and the 60s for time series analysis. And so there's a long series of long papers by these authors, Slepian, Landau, and Pollack in the early to late 60s all the way into the 80s on essentially this problem. And these guys worked for the phone company, and they said, well, their Earth was a minute of a phone conversation. Their maximum spherical harmonic degree was a bandwidth of transmission, which is why the phone sounds so bad compared to normal speech. And their problem was, their partial observation was, it's a finite length signal. So they tried to figure out how much information can you cram into 1 minute of a noisy, band-limited phone conversation. And this was a whole series of very theoretical papers. Also, Claude Shannon was involved in them, who basically tried to figure out how to efficiently send information, and then if you received it on the other end, how to recover the signal. So this is exactly the same problem, except ours is on the sphere. But we basically took all of their ideas and wrapped them on the sphere. And that's why they're called Slepian functions, and that's where you go look for the first references. So we're going to use these new functions, and we're going to still try to explain the data, but we're going to try and expand the unknown solution into that new basis. And in order to combat the ill effects of, the observation at altitude, the incomplete domain, and the noisy observation, we're going to truncate our solution. We're still explaining the data, finding the signal that best explains the data in the mean square sense over the observation domain, keeping it to a minimum. And our estimated signal is now the unknown expansion coefficients, which we solve into this new basis. And we could go all the way up to the bandwidth squared in this case, but we're going to find some point at which we can stop. And that point at which we can stop is like in the phone company problem is, well, how many pieces of independently recoverable bits, if you will, or units, which are maps now of information, can you send over such a noisy, band-limited and time-limited transmission line. And once again here, the statistics of the signal and the noise itself dictate to what level we can take this expansion. If we take it too far, our noise will start dominating. If we don't take it enough, we will not know enough about our unknown signal. So this is the last of the theory slide here. This is in a nutshell summing up what these new functions do for us. They're the eigenvectors of this lack of orthogonality operator. They actually turn out to be an optimization of something. They actually maximize the signal potentially recoverable from the region, in the region R of area A. And this Shannon number, named after Claude Shannon, is actually the sum of the eigenvalues of the optimization problem that you get out, which is the effective dimension of the space for which these units are a basis. Now, I know this is abstract. So we're making new functions. They're a linear combination of the good old spherical harmonics. And it's that linear combination that maximizes their energy in the region. And when you do that, you are led to a variational or an eigenvalue problem that you get a whole new series of basis functions, all of which are combinations of harmonics. And how many useful ones there are is this number. And that's the original dimension of the spherical harmonic space, but it's now reduced by the fractional area. So let me take an example and say that I showed you pictures of a spherical harmonic expansion of the gravity field to band limit 60. That meant there were about 361 functions with coefficients talking to produce that picture. If I want to get the same spatial resolution but only on Greenland, then I can multiply the 361 number here by the fractional area of Greenland, which is like 5% or something. And that will mean that if I want to represent the signal over Greenland to the same spatial resolution, the same every wavelength of detail, that I can do this in about 18 functions, which is very efficient from the inverse standpoint, because it tells you rather than solving for 400 coefficients in this regularized, ill-determined way, go find the 18 ones that you know ahead of time will be important because you're working with a limited observation domain. And so clearly that's back to the phone company, where if you could find the basis that was good for a minute of a phone conversation at a certain bandwidth, then you'd use that basis for encoding, extracting, and inference on the back end. So that's it. That's the mathematics behind it. We have concentrated in space something that was a spherical harmonic, which was everywhere, wiggles around the sphere. We have this many to begin with, up to some maximum bandwidth, L+1 squared. And we've, by this process, we've reduced it to formulating an unknown with only k functions, and the k is exactly the original dimension reduced by how little partial coverage you have on the sphere. And if you don't do it, you suffer the consequences of these effects anyway. So knowing that that's what happens to the information is very beneficial. So if we try to construct such a basis for the full bandwidth of Grace's solution, they typically give us 361 coefficients, and so 60 spherical harmonic degrees is what we get out of it. That's the bandwidth. If we try to find the best fitting spatial function that describes Greenland, then here's the very, very best we can find. This is super well concentrated at an eigenvalue of 100%, 1. The second best, the third best, the fourth best, and so on. By the time you're at the 12th best, you've concentrated 93.5% of the signal inside Greenland, and the rest is outside. So this more or less number, 12, 15 functions, will altogether be a good basis to represent whatever happens in Greenland. And we will not worry about the rest because they have energy outside of Greenland and they're just picking up noise, which we don't want, and in a region that we don't care about. So that's the general procedure. We're going to first try to learn as much as possible about the noise. Then we're going to design this basis I just showed you. And then we're going to do experiments with, well, we can choose the bandwidth, maybe what the NASA labs give us, which is 60. Well, they used to give us 72. Maybe one day they'll give us 50. Maybe there is some leeway here. There is a modeling step involved. And that's the first free parameter, is how much information do we really want. And then we experiment with small buffers outside, and we look at how the statistics of the estimation behave in extensive synthetic. And then we simply project the signal, or the data, the noisy data, onto this basis. And when we do that, we concentrate the information into a handful of functions with an increased signal to noise, and then we reconstruct estimates of whatever happens to the mass balance. So that's very different from what other people did in the GRACE community, but it's very, very close. It's in fact identical to the stuff that these guys, Slepian, Shannon, Wiener, figured out in the 50s, except they were working in time series, and we were working in spatial series on the surface of a sphere. Ideas from there. So looking at the noise, maybe I'll just say one thing about it to the first pair of pictures here. This is one noise covariance centered on Greenland, and I don't know how well you see it here, but this point in Greenland covaries with all the other points of the sphere according to the color in this map, and it's normal to 1 at red. So the point is that if you take into account everything that you know about the signal, that the mass variation in Greenland statistically depends on whatever happens in Africa. In fact, it's anti-correlated with stuff that's picked up there and here and there. And so all these stripes in the data that we saw earlier are manifestations of the fact that this one point in Greenland where we will make inference about whatever the mass is doing is actually statistically correlated to everywhere, which we know because we've done the full modeling. And when we don't model it the full way, which some people do, you actually have a wildly optimistic, symmetric, smooth picture of this covariance. And so this is sort of supplementary material here, but if you ignore off-diagonal components in the covariance, you have an optimistic picture. It's still not looking very good. If you model everything, you realize that everything varies with everything. So to do the proper estimation, you have to take this full covariance structure into account. We've just constructed the basis. Here is just a repeat of that. And then we project the signal, and this is now the actual inverse step, onto this basis. And now I've re-ranked them. So this is how the 11th function feels the changing mass over Greenland, and its average over the area is minus 72 gigatons per year. The third function is scaled by minus 46. That's how much that pattern is losing per year in the decade of observation. The first one is the symmetric best candidate function. Well, actually, that's the third most important in this expansion, and then so on. So these are the pieces of the data that project after this procedure of learning about the noise and projecting onto this ideal basis, each of which is like a little map that tells you, well, in this map shape, this is the magnitude of mass loss for Greenland. So when we put them all together, of course, we have, I'll skip that, we have a final total estimate of, well, what's happening over Greenland, and that is this map here. This is an update. No, this is the original figure of a paper that just came out last week. This is 8 years of Greenland, And so we're seeing in this estimation procedure, scaled and on a scale of equivalent centimeters of water, what's been happening to the mass of Greenland. And for the first time from I think for the best time, from just gravity, we're seeing some realistic spatial patterns where the mass loss is actually concentrated on the rims of the continent where we expect the glaciers to be really shedding the mass. And we're actually seeing an increase in mass in the center, in the highlands of Greenland, which continue to receive precipitation in the form of ice and snow, and which actually over this decade have continued to accumulate mass. But on average, when summed all together, there's about 1,500 gigatons lost in this decade. So we keep this up. If you're interested, we constructed a website called Polarize, also known as Greenland, at Princeton. And so in the time since the paper came out, which of course with its long review process was until 2011, now it's in 2012, we've lost another 500 gigatons of ice out of there. If you want to sum everything up and just look at the trend, well, then you get a graph that shows you the seasonal variations and their uncertainties, and then the best fitting slope. This is the rate. 200 gigatons per year of mass of ice is lost of Greenland. And here's the update. It's gotten worse a little bit because there were some particular big losses early on in 2012, and now our current best estimate, and it evolves every month, is 211 and some. For those of you who have followed it, there were some reports around 2009 about an acceleration in the mass loss, which made all the newspapers printing the news that's fit to print, and they were seeing 30 billion tons per year squared of an acceleration. But in our interpretation, they were just, looking here, and they had a particularly bad year, and they really overcalled the acceleration of mass. If we fit an acceleration, then we also get a little bit, and it's statistically significant. There's about a 10 gigaton per year acceleration that we think we can confidently call. But you can judge for yourself that most of this mass loss is pretty steady. And of course, this has all the implications of it that I'm not talking about, because when there is an acceleration, you have to explain it glaciologically, and when there isn't, you have to also be willing to go there. So what we've learned about Greenland, what I've learned about Greenland is that early estimates, and I didn't walk you through the literature because of time, but if you opened Science Journal or Nature Journal in 2006 and 2007, you would hear mass loss in Greenland is 100 gigatons per year. And you open the next journal and say it's 200 gigatons per year. And then the third one would be like 98, and then the fourth one would be 150. And all of them were quoting their simple averages over 6, 5, 7 years, spatially average over all of Greenland as a single number with a very overestimated and thus very small uncertainty. So they thought 5 years ago that the total number, the average number, was known much better than could be possible, because two labs using the identical same data would have numbers that varied by a factor of 2, each of which claimed to be within 10%. So now I think we've properly realized that this is also a question of statistics, and we found, I think, a better way of modeling it. The no hint of acceleration is probably a little strong here. 6 months ago, we didn't play much with a very small acceleration. Now the acceleration has actually grown a little bit. We can make of that what you want. But the bottom line message is that overall, there's still 200 kilometers cubed per year of ice being lost. But we now get interesting spatial patterns that we can try to link to climate models, to glacial models, to what actually is happening on the ground at a scale both in space and in time that is much better resolved than before, thanks to these statistical modeling approaches. So in other words, we get maps as a function of year. And so for I think, confidently the first time we're seeing actually that these maps are sort of peaking at the right space point and the right time points to be corresponding to what we think is happening on the ground. And it's no longer just a broad average that agrees with what everyone agrees, which is this 200 kilometers cubed per year, which has been around for a while. So we can now compare also with GPS surveys, which of course have the same wants. They want the mass, but they'll observe what the surface is doing. What we're getting from GRACE, and we're only using GRACE data in this study, is, well, what the potential is doing, what the ultimate density effect is. So I'm going to maybe just give you a few more minutes, if I may, on some things that you can also do with these Slepian type functions. This is what I just did. Got data, learned the noise, form a band-limited expansion with these new functions which are targeted to a particular region, and you'll do a good job, is the message. The second type of problem, which I actually worked on a lot, is a very different inverse problem, which says, get some data, learn the noise, assume, in this case the universe, could be anything now, assume the universe itself is a zero mean random process, which we are interested in studying in the squared way of trying to find out the power spectral density, which is how the individual spherical harmonic expansion coefficients together have a certain variance and covariance. So this is nothing but the traditional power spectral density under a model that it's really isotropic, so only dependent on the degree, and that there's no coupling between degrees. This is sort of the standard model of observational cosmology, that the universe is doing that. And our problem will be, well, find that from this data, which isn't the same as finding the expansion coefficients in the basis and then squaring it, because we're actually trying to estimate the square of something which has a very different statistical structure than the best estimate of the square property here is not the square of the best estimate of the linear property, which one reviewer of our paper thought for a while. Then they read it, I think. So here's what I think many of you are doing. You're taking data, you're multiplying by spherical harmonics. They've now become complex. You square them. You sum over the orders. You think that every possible orientation is a good candidate to give you a wavelength-dependent information. And then you normalize, and then you noise correct, and then you have the traditional power spectrum from spherical harmonics. But I've just tried to tell you that if you don't have whole sphere data, you have all of this coupling going on and you have all of these problems. So you're never going to actually do this, because if you don't have full sphere data, then you can show that that process gives you a really terrible estimate of the power spectral density. This is how terrible it is. If you just replace the omega by the data availability, and then you normalize out the area. So in principle, this should give you an estimate, just like in time series. This actually has a really terrible statistical structure, which is why nobody in time series multiplies by a boxcar, but always, demeans and tapers and does a little fiddling with it. So, terrible. Tapering at the edges. Well, what we're now going to do, all we're doing is we're sticking in one of these Slepian functions, some alpha, and so we pretend it's global data. And even though we only want the region, we're just sort of coming at it smoothly and then coming out of it smoothly again. And that has a great bias. It introduces a little bias, but you gain some certainty with it. And then what we really are going to do is we're going to do this for all possible of these Slepian functions, weight these individual estimates with the eigenvalue and then average the results, which is something that in seismology and in other areas, lots of people are also doing. Instead of doing a boxcar, use a taper. Instead of using one taper, use a lot of tapers and average the results. You get some bias, you reduce the variance, and you get a very stable estimate. In cosmology, this is what people do. This is what they want, a power spectrum as a function of degree. some normalized power spectrum, and then they fit curves through it with parameters that tell us something about the universe. Well, so here we just did this in our last few slides about the Martian magnetic field. This is a map of it. This is just a radial component, and it's got lots of interesting structure. But how can we study it in spherical harmonics when, it's all or nothing? We know there is a huge crustal dichotomy. The north is very different from the south. We can see with our eye that this region of Terra Cimmeria is very different looking structure than anywhere else. We can start looking for particular patterns. And so this is exactly what we do. We just design for every one of these regions their particular best basis and use them as windows before doing spectral analysis. And then we can pull out, compared to the global power spectrum. Once again, this is spherical harmonic degree, so long wavelengths here, short wavelengths there. This is power. Here's the global spectrum. But now we're seeing, if we just look at the cap, or everything but the cap, or the south of the north, that the spectral signatures are very, very different. And no wonder there is non-stationary variations of it, but we would never see it from the global pattern, where we can pull it out and their difference by this technique of localization. And so we did a study where we looked and tried to model on a grid all the various pieces of little bits at a time, essentially a spherical cap, and designed a basis for that, and rotated, put on every space point, and then did a little two-parameter inversion for an equivalent depth and an equivalent source strength of the Martian magnetic field. And here I'm showing you three very different such spectrum. One is very high up and saturates very flat. One of them is very low and rises slowly, and the other one is in the middle. And this is a 45 kilometer deep 0.005 nanotesla square. It's actually minus 11. It's up in the air. It's very small. This is 57. So these are just 3 points that are very different to show you that everywhere on this planet you have a different behavior, and we can model, because here we fit this particular behavior with a two-parameter model, which is some sort of equivalent source distribution for a strength versus decorrelation depth for the lithosphere. And so when we do that we do this for everywhere, and we plot the magnetic strength versus the depth in this graph, and the color coding is here how well we fit the particular spectrum. Then we analyze how depth and strength co-vary and what their air ellipses are. But then most importantly, we look at how this source depth of magnetic anomalies plots against the crustal depth, which is derived from gravity, which is some estimate of basically the thickness that has nothing to do with the magnetic field. So the thickness of the crust correlating pretty well. It was definitely correlated. It's not one-to-one, but correlated with the depth of the magnetization. To us is, the first piece of indirect evidence that actually, when we pick up different strengths, different layer thickness, so in other words, different volumes of magnetized crust, that probably has something to do with properties of the crust, more so or in addition to whatever may be an imprint from the core. But when we say that, we're referring to this graph, which shows a correlation of magnetic crustal thickness with gravitationally bathed sort of MOHO crustal thickness. And so that's it. I mean, we're developing mathematical techniques to properly estimate mass changes in the Earth system, apply to Greenland, where we get spatial resolution, temporal resolution, and error bars that are better, more realistic than we think was done before. It's all sort of rooted in this inverse theory framework with concentrated Slepian functions, which comes out of well-established time series methods. And when we look at a Martian magnetic field or some other planetary field, we can do local analysis and aren't stuck with it's either all the globe in spherical harmonics or it's Cartesian. No, we can actually do we can meet the local with the global. And well, that's the value of that graph that I just showed you last year, is that this correlation of magnetic source depth with some crustal structure is to us a bit of an indication that the crustal column is actually responsible in generating the observed magnetic field, as I said, more so or in addition to whatever core signature there may have been to begin with. Thank you.